in this lab, we're going to be doing several acid-base titrations. The acids that we're going to be using are weak acids, and we're going to be reacting it with sodium hydroxide, a strong base. The first set of titrations that we're going to do is we're going to do these titrations to what we call standardize the sodium hydroxide. So we have a solution of approximately 0.1 molar sodium hydroxide, but we want to figure out a more precise concentration. And so in order to do that, we're going to react potassium hydrogen phthalate, KHP, with the sodium hydroxide, having measured the KHP to a precise mass, and use that mass to be able to figure out what the precise concentration of the sodium hydroxide is. And then in the second part of the lab, once we now have our standardized sodium hydroxide, we are going to do another set of titrations using an unknown acid, except this time we're going to monitor the pH over the course of the titration and then plot the data to generate a titration curve. From that titration curve, we can figure out the Ka of the unknown acid. So in order to do a titration, the equipment that we want to use is a burette. So that's what I have here. This is simply a burette clamp. And then the stopcock, this is the stopper that I can open or close. And then you see here that I have a beaker. Now the point of the beaker is simply just in case I ever accidentally leave the stopper open. I don't want to have sodium hydroxide get all over the place. So that's the point of the beaker. It's just proper safety procedure to always have a beaker there. I can use this clamp to lower or raise the burette because it is important when reading a burette that I am eye level because I need to see exactly where the bottom of the meniscus is. Now, I do have a funnel at the top of my burette so that I can more easily pour the sodium hydroxide. All right, so to start with, I'm going to add just a little aliquot of sodium hydroxide to rinse the burette. Now, the point of this is that if there's any water that's left over in the burette from someone previously using it, that water will dilute the sodium hydroxide. And remember, the whole point of these first titrations is to standardize the sodium hydroxide and figure out the precise concentration. So I don't want any water left over in the burette. So all I need to do here is simply add anywhere from 5 to 10 milliliters of the sodium hydroxide solution, and then just let that drain out. So I'm just rinsing the burette, and this sodium hydroxide is just going to be discarded into the waste. So I'm just going to let this drain out, and then I'm going to do this one more time just to, again, ensure that there's no water left over in the burette that could dilute my sodium hydroxide. And so you can see it's really not necessary for me to precisely measure out the sodium hydroxide in this situation because, again, I'm just rinsing the burette. Now, while that's draining, what I have here in this flask is a solution of the KHP. So I've already weighed out the KHP and recorded that mass in my lab notebook. I am going to add a few drops of my indicator. The indicator that I'm going to use for this lab is phenolphthalein. And so phenolphthalein will start off colorless, but it'll turn a pink color once the titration is done, once we reach the equivalence point. Okay, so now that that's rinsed, so now I am going to add in my sodium hydroxide. And then what I want to do is I want to look at the bottom of the meniscus and read the burette. Now, as you can see in the lab materials, we read a burette going down. It's the opposite of a graduated cylinder. So in a graduated cylinder, it's 0 at the bottom and then the numbers go up. But for a burette, it's 0 at the top and the numbers increase as I go down. So the last number on here is 50. The 0 is up here. So when you read a burette, not only do you need to be eye level, you also need to remember that you are reading it going down. And then remember, we're looking for the bottom of the meniscus. That's the reading that we want to have. So I'm looking at this, and what is also sometimes helpful is to put a piece of paper behind it. Just allows you to see the numbers a little bit more easily. So it looks like I'm at 9.95. So that's the level of precision that I get with a burette. I go to 2 decimal points. So that's another reason why we use burettes here, is because they are more precise than graduated cylinders. Now, the reason I have a piece of paper here is not just to read the back of the burette. It's also to help determine when I have reached the end point, because it can be a little difficult to see the color like this on a black surface, but if you put it on a white surface, it actually makes it a little bit easier to see that pale pink color that we're going for here. So what I want to do is I'm going to open up the stopcock slowly and then swirl as I add the sodium hydroxide. I'm really not looking at the level of sodium hydroxide as I go. I'm really focusing down here so I can look at the color, because I want to stop when I get to that pale pink color. So it can sometimes take a little bit of trial and error here to get the right rate of addition. You can certainly do it drop-wise like this, but we also do want to balance time and efficiency here. So drop-wise, we don't need to start off drop-wise. We can open this a little bit more. And you see the pink color appears, but then immediately disappears as the sodium hydroxide reacts. And so when that pink color starts to persist and it takes a little while for the color to fade, that is when we want to slow down the rate of addition. But it is important, you see here I'm swirling as I go, because I do want to make sure that it reacts quickly. So it's starting to linger a little bit. I want to slow it down just a little. Okay. And it does take a little bit of patience here. Now, something to keep in mind, we're going to do multiple trials because it is easy to go past the equivalence point and get to more of a hot pink color. So the point of doing multiple trials is to get better data over the course of the experiment. So we'll do a total of 3 trials for a titration, because for the first titration, it's easy to go past the end point. I mean, it's lingering, but it's still kind of getting there. So again, just at this point, probably doing it closer to a drop-wise addition, just to make sure, because it really only just takes that one extra drop to go from pale pink to a hot pink. And we really do want to try to avoid that hot pink color. And so there we go. So now we can see we're at that pale pink color. So now what I want to do is I now want to record the final volume of the sodium hydroxide. I'm going to slip this out here. And so for the final volume, we are at, let's see, 32.80. So I would then record that volume as my final volume. And then what I'm interested is the change, right? How much sodium hydroxide did I add? And so I'm going to use that value to figure out the precise molarity of the sodium hydroxide. So as I mentioned, we would need to do this 2 more times. So weigh out the KHP acid again, add more sodium hydroxide to our burette, and again, record the initial volume and the final volume of the sodium hydroxide, and then use those values to figure out the molarity of the sodium hydroxide. Now, for the second part of the experiment, as I mentioned, we are going to monitor the pH using the pH sensors that we did previously. So that would be using the LabQuest and the pH probe. That's what we're going to use for the second part of the lab. So I would insert the pH probe into the flask. And as I do the titration, I'm going to record the pH. And then I'm going to plot that value to generate a titration curve, and then use that titration curve to calculate what the Ka value is of my unknown acid. Because for part 2, it is an unknown acid. It's not the KHP acid. So procedurally, it's the same in the sense that I have sodium hydroxide, I'm adding it. But instead of looking for that pale pink color, I'm simply going to be monitoring the pH using my pH sensor so that I can generate my titration curve.